Hello everyone, welcome you back to the third module of electromagnetic theory and interference course. We are discussing waves in general in the previous session. Today we will solve a problem and let us see the electromagnetic wave propagation in different medias. So the problem that is given is electric field in the free space is given. So electric field E is 50 cos 10 power t plus beta z into the unit vector ay volt per meter. So they ask us to find the direction of wave propagation, to find beta and time the wave takes to travel a distance of lambda by 2, as well as they ask us to sketch the wave at different time periods. So by seeing the given expression of electric field and by noticing this angle part, see this is cos of this actually E naught cos of omega t plus or minus beta, whatever direction it's given, we can take it, right? Beta x here. So if you see the positive sign in beta, we can infer that along with beta, whatever component is given, along that particular direction only, wave is propagating in the negative axis, right? So along the negative x direction only, wave is propagating. So that is the first solution. And and they have given one more hint that electric field is in free space. So in free space, velocity of electromagnetic wave is equal to the velocity of light, right? So from that we can find beta, as we know, omega by u. U is c here. So omega from this expression, comparing these two, it's 10 power t divided by the velocity of light. We can get 1 by 3 radian per meter. And we know that time period of a wave, if t is a time period, it takes t seconds to travel a distance lambda at a speed c, and they ask us to find the time to travel a distance of lambda by 2. So I have to divide the total time period by 2 to get the this particular time period. Okay. So if we know the relation, right, t equal to 1 by f, and we know the relation between omega and f also. So if you find the f from here, it is omega by 2 pi. Substituting here, we can get the time period in nanoseconds. And the last part is we have to sketch the wave at different time periods. For t equals 0 in this expression, if you substitute this t, this component vanishes, 50 cos beta x only will be there, right? And that only they have plotted here. It's the cosine wave, okay, at this particular point. And t equal to t by 4. Since wave is traveling in negative axis, I have to take the t by 4 in negative axis, right, that quarter period. So if I substitute there, the electric field intensity will be 50 cos. Why we have put a mention as EY? Because the component of electric field is along the y-axis, but wave only traveling along the x-axis, negative x-axis. So EY is 50 cos omega, it's 10 power 8. For small t, I have to put t by 4, right? And the t by 4 I can substitute in this way. 2 pi by 4 omega by this relation, yes, plus beta x. So if you cancel the similar terms, we will get beta x plus pi by 2. We know one geometry that cos of phi plus or minus pi by 2 is nothing but for cos phi plus pi by 2, it is minus sine phi, and if it is cos of psi minus pi by 2, it is plus sine phi. Here it is positive, so I should get what? Negative sine beta x, and for the negative is coming before. So we can see from this graph, it's a sinusoidal function, and at this point, okay, if you take my wave is sinusoidal, see the origin and write the function, but seeing the amplitude, it is negative. Okay, just we are drawing the wave as for t equal to t by 2, if we substitute in the given expression, we get 50 cos of beta x plus pi we are getting. We know the property that cos of angle plus or minus 180 degrees nothing but minus cos of the particular function they have given. So it is going to be minus 50 cos beta x, right? So, if you see at the origin points, again it is coming in the cosine function. First it's a positive cosine function, and then it turns out to be a negative sinusoidal function. Yes, it's starting in the negative, right? And again negative cosine function. So we have to represent the point P at a different time period, 0, t by 4 and t by 2. As we can see, wave is in moving in negative x-axis. Okay. So, let us learn about the electromagnetic wave propagation. To understand the wave propagation in different media, we have to consider the medium properties like conductivity sigma, permittivity epsilon, and permeability mu. So, in free space, we know that there will be no conductivity, so it's zero. Permittivity will be equal to free space permittivity epsilon naught, and permeability will be equal to free space permeability, that is mu naught. These are the constant, we know its values. When you go for lossless dielectric, since it's lossless, okay, there will be no conductivity there also, approximately it's zero. Permittivity and permeability both depends on both the relative permittivity and permeability as well as the free space, and here the conductivity will be very less when we compare to omega epsilon term. When you go for lossy dielectric, there will be a little amount of conductivity, okay, and it's not equal to zero when you compare these two. And the rest other terms remains the same. Permittivity, permeability remains same. Only the thing is conductivity is not equal to zero as we compare with lossless. When you go for good conductors, conductors will provide me good conductivity. So the conductivity will be approximately equal to infinity, and only the permittivity is equal to free space permittivity, whereas permeability depends on relative permeability as well as free space. And here, as we can compare lossless and good conductors, lossless dielectric and good conductors, you can see conductivity is very large when we compare with omega epsilon. So why I highlighted this lossy dielectric means we are going to see the wave propagation in lossy dielectric first. There in this case the conductivity is not equal to zero, and this is a general case. And from this we can understand how the wave is propagating in other three media. First, we will study about lossy dielectric in the next upcoming session. Happy learning. Thank you, everyone.